We already come to the last task, which is also the biggest one, computing path EOTX. Here we have two different networks where we calculate the distance metrics for, so now it's path metrics, not only link metrics. The first one is called 2 hops with overtake opportunities, and the second one is called the diamond network. If you have watched my lectures, then you'll maybe recognize those networks from the opportunistic routing part of it. So they are very similar and similar in nature to those two cases from that bring benefits in opportunistic routing. So the first one, skipping hops; the second one, multiple independent forwarders. Where in skipping hops one can use an overtake opportunity with a direct link, and in the second case, the multiple independent forwarders are all relays where a node has a weak link to. At least then it is especially useful to use opportunistic routing. So again, I show you the networks here. So we'll have a strong path here to the front, and weak links where the strong path can be overtaken. And then here in the second topology, the diamond network, we can see there are weak links towards a multitude of relays where we can use the features of opportunistic routing. So we start with the first subtask, which is actually computing the ETX, so a single path metric. I circle the node that we are currently using as a relay, as a next hop, and we always start with that one with the lowest distance metric, which is in the beginning only D itself. We are calculating towards D, so D has a metric of 0 to itself, and we can then update those two nodes here. So the distance of R1 to D can be updated by calculating the link metric and adding 0 to it, so it's 2.5, and R2 can be updated via adding 1 to 0. So the updated path metrics are 2.5 and 1. S has no connection until now towards D, so it's still infinite. Then we use the node with the lowest distance again. D is already out, so we use R2, which has a distance of 1, and circle it now. We can update the nodes that are connected to it and are not marked red right now. So we calculate the distance of R1 towards D using R2 as a relay. The outcome is 2 because we add the link metric to the distance of R2, which is 1. The result is 2, which is smaller than using the direct link here. So we can update the path metric to 2. And obviously we can update the distance of S because 3.5 is less than infinite. So at the last one, R1 has a lower path metric, so it was 2 compared to 3.5, so we use this to update, and we can then update S distance, because it's the only node remaining, to 3 using this path here, only using the perfect links. So that the ETX, the distance single path, is 3 for node S. For the second network, the diamond network, we again start at the node with the lowest distance metric, which is 0 to itself, and then we update all the incident nodes, which is R1, R2 and R3. They all have the same loss probability, 0, so we can all update them to having a distance metric of 1. Then we choose the node with the lowest distance metric, which is each of them, and it doesn't matter which we choose. Always the distance and the single path distance over any of the nodes is 6, because the ETX for the link here, for each of the links, is 5, and the remaining distance is 1. So now we are already finished with the first task, and we come to the second task, where we compute the EOTX metric according to the algorithm you find in the sheet. It looks quite complex. It's actually not super hard to do, but you really have to keep track of all the symbols and their values, because you update them. They change their values, and you have to always use the right one to not make a mistake, which then draws until the end of your calculations. So just like before, we use this Q set called O in the algorithm. You find it here, where we put all the nodes into it, and then we always extract nodes from that set. Where min means the minimum distance. So I wrote down the set here, then the distances we have calculated until now are here, and just as before, always we start at the destination node, because it's the node with the lowest distance, always 0 to itself. So we extract d from the set, and we can start now. So in this set now k, in this step now k is d, and then we just cycle through the remaining nodes that have a direct connection to our node k, so to d. Those steps here are the core part of the algorithm, and I put it just below here so we still have it in mind. As I said, the table now will look very crowded, because I always put every of those symbol values into the columns of the algorithm, just not to confuse them with others, or to having to look it up somewhere else. So at first we look up the values for R1. R1, where the initial guess here is still valid, so we haven't calculated, so we use 1 here, and the connection of R1 to D has a loss probability of 0.6 and a success probability therefore of 0.5. I know it's very easy to calculate this, but it's easier to keep track if you just write everything down like this. So we start by calculating T. We just use the formula from below here. Still the distance of k to itself, of k to d is as it is from d to itself 0, and so t stays like it is. The value for p changes. We can just very comfortably look up the values here and fill them in, t and p still being the initial guesses, and then we can update the distance of R1 to D. So this one is nothing else than the ETX value for this connection here. It's clear because there's no multipath, no opportunistic connection going on until now. So the second incident edge is here, so we update R2. Again, we look up the values, write them down, and use the initial guesses because R2 was not updated until now. We know that the link is perfect, so this is 1. It does not change t in the first part because we still the distance from d to itself is 0. As the link is perfect, also p is 0 now, and the distance of R1 is 1. Again, it's the ETX value because there's no multi-path opportunity until now. This changes when we extract the next node from the set O, so the minimum distance now is 1 towards the destination node D, and therefore we extract R2. K is R2, the distance of R2 is 1. So now we can again cycle over the incident nodes, which are R1 and S. And as I said, we now have a first multipath opportunistic opportunity here. So R1 can skip a hop if it chose R2 as a relay. The 40% of the packets that directly go to D, R2 would not need to transmit. So from perspective of the algorithm, we choose the take the t and p values that we have calculated before. So t was 1, p was 0.6, so the t values for R1, not for a different node. You write them down here, and then we check the link, which is a perfect link in this case, and we can calculate the updated t and p values according to those formulas like here. Doing this and then putting those new updated t and p values into the final equation of the distance, we get a distance of 1.6, which is a lot less already than it was before. So using R2, or alternatively, depending on the reception, is already a big gain for R1. So the second incident node for R2 is S. This would now reflect a single path over R2, as this is the first update for S. So we can check the result of our calculations here. I'll not repeat the step by step but we can see that the distance of S to D, just using R2 as a relay, so just using a single path, is 1 plus 2.5. So we can check this calculation here for the first one, for the first update, via calculating a single path. So now R2 is already used as a relay, and the incident nodes are calculated. So we choose the next one. Next lowest distance is 1.6, as it was just updated, which is lower than 3.5 for S. So we extract R1, write down all the values as before. I think I've done this now for some steps, so you can see the solution here. And the updated distance now for the only node we can now cycle through, which is S, is 2.36 as opposed to 3.5 before. So by using these overtake opportunities here, which we have, so not always using S as a relay, but sometimes skipping over through R2, and when R2 is sending, sometimes skipping, and when R1 is sending, sorry, sometimes skipping R2 is relay and directly using the received messages at D, we can save some transmissions. I'll come to this in the third subtask with more detail. Now first to the next network. Again, we start at the destination node because it has the lowest distance, 0 as opposed to infinity. Then we update all the incident connections. I used the quick way here and used just j as a variable here because it's all the same calculations. Again, also it's the first update for R1, R2, and R3. And it's always a perfect link, so the distance, well, should be 1 always. So now as D is already used and extracted from the queue set O, we can extract the next node. So building a single path now from S to D over R1, and the expected result is 6, as it was before in the first subtask. Now we extract the second node. As the distance is the same for every one of those, the order doesn't really matter. But now the result changes. So now S would use both of those nodes as relays, and consequently the distance that we calculate is a lot less than it was before. And if we include the last node, then again using the t and p values always from the last update, remember this, we get the result of having an EOTX of 3.049, which brings me to the last subtask where we should compare the ETX and EOTX metrics that we have calculated for both of the networks for each traditional and opportunistic routing, so for ETX or EOTX metric. And we can see that for the nodes that are directly connected through a perfect link, there's no change at all. There's 0% gain, where the gain is actually a percent gain, so it's the actual improvement. Where we can see that for node R1 and just cycle back. So for node R1, if it uses R2 as a relay whenever necessary, but the transmissions that directly go to D are used, then we can save up to 25% of transmissions. Meaning we can save this if everything else goes smoothly. If the conditions don't change and R2 only then forwards when it needs to. R2 only then forwards when it needs to. So the gain for the source node here is even a bit bigger, with 27.12%. The situation is even a bit better for the diamond network. So if we have a multitude of weak links, which had a loss probability of 80%, and those have good quality forward links, we can save up to 69.79% for the source node. If we use this, if we use any of the relays to forward, just depending on whichever of those nodes have received the message. So this was the results for this exercise. I hope you have understood what I was talking about, and I hope you can, if you have not solved it before, now recreate the solution of the tasks. The next event for the wireless mesh network part of cooperative communications is a hands-on workshop I hope to do with you. It will take place in the next scheduled time of this lecture series. So this is 1st of July on 2:50 in the afternoon. Due to the current COVID-19 situation, we'll do this outside in the courtyard of Berghausenbau. So in the inner circle directly attached to the courtyard, well, directly next to the chairs rooms. If there's rain, we can't do a workshop because it's only safe for us to meet outside for the moment. And please bring your laptop to this, and questions if you have any regarding the lectures and the exercise. If you have something that might take a bit longer, you can always just email me and I'll answer your questions. So thank you and see you then.